The red brochure is on our undergrad program that I'm not sure many of you in here are seeking to go back to get another undergrad degree, but maybe, right? Wouldn't be the first time that we've had students go and start their degree program at age 30 and higher. Hopefully that'll sort it out. But otherwise, and more importantly, as you have contacts in your hometowns and so on, and with those folks in the prime year would be juniors in high school right now that are thinking about studying engineering somewhere. You know what this field's about and the wonders that this field has associated with it. This is something to perhaps share with them, some basic information to introduce them. We did have an applicant that was from Minnesota that was slated to start this last fall. They didn't come for whatever reason. They may have gone to another UM that you have locally here instead. But that's this. Now, so they're here. I'm not taking any of these home. So the wait staff, I guess, not you guys. The distance program may be somewhat of more interest to you all in that this is set up. Well, one thing at a time. This is set up again for practicing engineers. The entrance requirement is an engineering background. Certainly doesn't have to be in fire protection engineering. The program is all online, so that you never have to come to campus. In fact, we've had 3 graduates from that program now that the first time they ever came to campus was for graduation. So it's all online. Most of the people are from the United States that are in the program, though not solely. There are about 40 students in the program right now. That if you want to go and continue for a degree, it's 10 courses. It can take about 2.5 years. So you're welcome to come and take a class. There's a single class, maybe good title that interests you, whatever. So that's completely acceptable too. So those are here as well for your distribution. Take them back to your offices and leave them around for colleagues and so on. Okay. So a few of these tables that I'll fight with this projector that I'm not sure why it's doing what it's doing. There are many more where these came from, certainly. Let's see what this is doing. That's kind of the last resort. Let's go back to this first of all.
We're fine here tonight.
Let's let me start over, unfortunately. But all right, so let me while this is doing this, because this is going to take a minute to reboot and so on. Excuse me. What I had planned to talk about was, as you've seen in the meeting notice, talking about evacuation models. The idea being that there's an interest in, for whatever reason, in a particular project, and there's an interest in using an evacuation model, and the choice is, all right, so which one do you use? They're all equal, they all give you about the same results. So yeah, whatever one's convenience, the one to go get is how we started this little study back a few years ago now. I guess it may have been 4 years ago altogether when we started this. There are about 25 models that exist right now, evacuation models. That some of these are in the public, more or less public domain. One of them you can get just by Googling the title of the one evacuation model. You can download it free of charge. It was originally developed with money from the federal government, so that's why it's free of charge. There's an assortment of others, though, that are proprietary, that individual consulting engineering companies have. and they use them for their individual projects, and they never see the light of day outside that office or outside of that corporation. And then that's better picture, finally. And then finally, there are the others that are available for sale. Though these are usually fairly expensive, the ones that at least I'm familiar with. So, you may do evacuation analyses for these kind of places, right? In performance-based design, where you're looking at an arena, as I'm waiting for this thing to come up. So you're looking at smoke filling sort of issues, and can the people off of the upper balcony level get out of there before the smoke has descended on top of their heads? This is particularly germane to university faculty, because we sit, and the students said, stand, right there, which is the kind of the way that the college arenas all seem to be designed these days. So we get a good view of the top of the banners that are up on the girders. This is soon to come to fruition, I hope. They want to go through this route. Yeah, that's the one.
I agree. What did Bill Lee say after we got the Nimrod stuff?
Too many virus checkers, firewall, at least that's what I think. I hope so. Slides, so you have some words that you can associate with some of these acronyms and so on.
Yep. Do you have your program on it?
I do. Here we go. Here, fine. But thank you for that offer. That's what did it, though.
It did, didn't it?
Yeah.
It's just like testing smoke.
I should have said that. I probably only did it the first time.
That one. Yeah. Or any time after the first time. Yeah, okay.
Is that your laptop?
This one.
You get out of bed to start this up, get a cup of coffee, and come out.
Right, that's why I didn't want to reboot it. But here we are at long last. All right. So the title is here, How to Obtain Credible Results, and maybe the better idea here is I want to talk about these evacuation models and just give you some sensitivity to a few of the issues that are involved in using these so-called evacuation models. And I'm sure that the group will be split at the end of the night thinking about these models in a glass half full or half empty sort of style in terms of their capabilities and what they're sensitive to and so on. And that's part of my interest tonight, I guess, just to make you aware of these. These are not plug-and-play sort of things that you just turn them on and go, and that's all there is to it. What's it take to run these things? So we picked 3 models to run through this little exercise. And then we wanted to get a sense for, if you run these 3 models that are relatively popular in the evacuation modeling world, that we had access to, that was an important constraint. We had access to at the university with our very modest budget, so that the 4 free models were ones that we liked a lot. But otherwise, as you run these models, can you pretty much just run them and run the default options, and for a generic, plain, vanilla sort of building, you get the same results. That was the interest that we had. That's how it all started. The analysis, I'm talking about the we, and this is the faculty member talking about we, that means the grad student really did the work. I have to give her credit. Erica Kuligowski, she's at Nick, well, she's now at the University of Colorado pursuing a PhD, just finished her first year there, though she's kind of detailed from this to do that. So, with an interest in continuing in this area, basically. We picked 3 models. The BACnet, this is one that was the one developed with the NBS, at that time now NIST money, from the University of Florida. X89, it's a model, was a model developed at NFPA by Rita Fahey. Model's never seen the commercial world, I don't believe. It's still very much thought to be a research tool as you talk to folks at NFPA. And they're very secretive about what their long-term ambitions are with this model. I'm not sure what their idea is. It's now been around for 17 years. It was developed in '89. That's the name. And then Simulex is one of the models from the UK. There are 2 models from the UK that get a lot of press and a lot of discussion, a lot of coverage, I guess, Simulex being the one of them. The other one that's really the premier model, I think, at least in terms of capabilities, is a model called Exodus, or building Exodus if you apply it for building. And I would love to apply this model, but that was well outside of our university budget to even be able to touch that. So that was unfortunately not one that we could deal with. So these are the 3 that we did. But let me give you a little background on each of these models, a little sense for what each of them do, and how to work with them. And these are all models, I should say, that we work through in our graduate program in Maryland. For example, in the resident program, the distance program, they dealt with the Evacuation model, I think is what Steve Gwynn just finished. We just finished our life safety class as part of the graduate program. I will say, one of the key advantages to the distance program that it took us a little bit of time to come around, and our whole marketing scheme was that a lot of people don't want to come to College Park, Maryland and spend a year or 2 years with us, and that's fully understandable given the assortment of constraints and so on. But we also came to appreciate the faculty don't have to be there either. So for this class that just ended, we have 3 of the world's experts in life safety. Dave Purser, some of you know from the toxicity chapter in SFD handbook, part of it. John Bryan, one of the big names in human behavior, and then Steve Gwynn, who was one of the principal developers of Building Exodus from the UK, though is now in Denver. So 3 guys that were one in Maryland, one in the UK, and one in Denver teaching this class. The students principally all around North America. Anyway, about that, this is a node-arc sort of model, where you're going to put a node in each space of interest where there may be people in it. And you're going to connect the dots by these arcs that are the pathways to get from one spot to another. It kind of looks like a sprinkler diagram in a way. Right? And the mechanics of the science behind this is very much similar to a sprinkler flow sort of algorithm. Right? In terms of getting the people, now you're not going out the nose, but the people are starting at the nose and they're ending down here at the exit. Okay? Kind of a reverse flow sort of thing that you're used to in sprinklers. And you have some basic things to put in. You have to say for a particular node, how many people can you put in there? 125, it says there at the top of the door for this room, if this would be a node. How many people were there initially? 32 or 3 of us, or whatever's the number we put in if we wanted to model this particular space. So we have to provide some information about the arc that basically deals with how wide that doorway is. Excuse me, but mostly in terms of how many people can we fit through that doorway, and how long does it take us to get from this node here to a node out in the corridor. You have to go through some velocity calculations for that. Right? How fast do people walk? Kind of situation. Now, BACnet, or BACnet 4 in the current version, is an optimization model. Optimization model is something that either minimizes or maximizes something. There are a lot of optimization models used in engineering. Not too many in fire, I guess, but a lot in engineering. BACnet goes through, let me come back to this flow diagram. EvacNet is an optimization model, and then it's going to split the people if there are choices on which way they go. And here there aren't a whole lot of choices. But if there are choices, some of us go this way, some of them go this way, and EvacNet will distribute us so as to minimize the evacuation cost. Okay? That's what EvacNet does. Somebody was talking before dinner about you do evacuation plans for your facility. And EvacNet sometimes gets used for that sort of thing. To identify the best route for everybody, kind of the thing you put on an elementary school wall of class room 101, you should go that way, and 102, you should go that way, and so on and so forth. But it provides minimum evacuation time. Simulex. One nice thing about Simulex, it has a CAD interface, so it's easy, relatively speaking, to provide to put the input together. And you can take your AutoCAD file from the architectural floor plans and bring that right into the evacuation model. And as such, it gets called a fine grid sort of model. So you're not just putting a node here and a node there, but every square foot of floor space basically is being considered. We have to say something about the occupants and how fast they're going to walk, and with Simulex in particular, it deals with walking speeds in terms of how big the people are physically. Kind of interesting style. Yeah, right. And that gets more interesting, actually, a little bit with another model. There's velocity-density relationship. They're all going to use velocity relationships about how fast do people walk. And this one comes from a Swedish researcher, Francis, from Lund University, as a fire protection program. This is the input for Simulex, and one of the things that Simulex does, and how does Simulex get people to the exit? Well, it's going to start a person here, for example. These circles here, multicolored circles, are identifying how distances from a stairwell. Right? So they're just rotating out, showing how far away are you from this stairwell or this stairwell. And the objective of the person is simulated. They're going to walk perpendicular to these constant distance profiles to get to the exit. Right? So that's how that one works. Simulex, this is what it looks like when you run it. That's not for this building, but this is what it looks like. Right? So you can see the merging flows with people getting queued up at the doorway. They're coming down the stairway here. Somewhat near the edges, but a bunch in the middle, much more than our research would suggest should be in the middle of the stair. But that's what it is. This is largely just a cattle run. Right? The people aren't talking to one another, they're not thinking, they're not helping each other, and so on and so forth. Somebody gets stuck right there. When you look at the thing just in general, you say, hey, it's about right. It gets a little crazy when you watch an individual, though, with our simulations of the hotel I'm going to talk about. When we started the evacuation, there was somebody that started in the room, in the hotel room, went into the bathroom and bounced around the walls of the bathroom a little while, and then found the way out. Right? Let's go beyond that.
Now, can I ask a question?
Oh, please. In fact, yes, please do ask questions as we go along. Yes?
Some of the things we've been hearing in the last couple of months have also been that some of the really big issues of firemen coming back up the stairs while people are evacuating. Can your models actually handle the counterflow of rescuers coming into the building while the other people evacuate?
In general, many of the models cannot. This Exit 89 can. It's one of the models that can do it. There's some work that's going on in this currently that's specifically trying to get some data on contraflows, post 9/11 curiosities and so on, but the EvacNet doesn't touch that. Simulex, I don't think, touches that either. But that's a very, very relevant question. Exit 89, the input for it, it's a no-march situation like the EvacNet. We don't have to do that one again. One of the interesting things is you have to put the body size of the individual in. Actually, I have to say, unfortunately, there's a typo here. Which is the more interesting thing.
We're 2.8.
No. glad you're asking questions, because otherwise we would have completely missed it. But, you know, the interesting, how much has been in the news lately about the obese Americans?
Yeah.
Right? And here we come out to be the smallest of the three. And say, well, where the smallest person is going to now move the fastest because it's a less dense flow. Okay? So we're going to be the quickest because we're so thin and tough. And so kind of, you know, that's one of the points, though, that for a lot of U.S. consulting engineers, you're here doing this work, you say, we're doing this with American projects. That's clearly right, an American population without thinking of the implications of that. Action 89 also has the capability to run at a normal travel speed, so kind of a walking speed based on drills, fire drills, and so on. Emergency travel speeds are an increase of nominally 50%. This is based on some work that were done by a couple Soviet researchers back in the 70s that suggested there was this difference, though I don't know that it's ever been confirmed in any Western study, right, or any study after that, anywhere. This one does allow to bring in some smoke data from CFAS, for example. That it's smoky, it's hot, it's whatever that maybe causes some issues. All right. The building we looked at, and all in the name of, let's do something simple and see what differences we get. Let's not look at the most convoluted building ever that there you almost surely are going to get some difference. So I thought of, let's just do a simple hotel building. Double-loaded corridor kind of situation, straight shot corridor kind of deal, stairs nominally at either end, and that's all there is to it. So that's what we worked with. The building itself is a 28-story building. You can see the details of it. Now, we only modeled floors 4 to 24, and floors 1, 2, 3 have a lot of ballrooms, rooms like we're in now, that would involve a lot of complications. We didn't want to get the complications. Let's do the plain vanilla building. So once the people got to floor 3, they were presumed safe for the purposes of our analysis. One of the quirks of this building is kind of interesting, where we tried to get a plain vanilla building, but when we got the actual file and so on from an AutoCAD drawing of an actual hotel that fit this, we find the landing on one stair is a little bigger than the other. So you end up with a little longer travel. For anybody who goes in, what we're going to see is a left-hand stair in the drawing. So that for somebody that starts all the way at the top, they're going to travel over 100 feet compared to somebody that runs down the right-hand stair. All right, just a little trivial fact. Tuck that away for right now. This is the building that we had some floor plans for from a major hotel chain. I shouldn't mention who in particular, as it is. So, I do a lot of conversations with guys at Marriott that are right down at, that's a different conversation, sorry. So this is the hotel, right? Now we had to adapt it a little bit because we don't want people evacuating down elevators or trying to go down elevator shafts, in case it may be. That skews the evacuation times a lot. There was a conference room, and we decided, we went back and forth. We said, we'll leave a conference room in. And otherwise you can see with a couple exits. Here are the stairs, here, and here. So nominally at either end, these are a couple suites sort of thing that you hear about people having. At State University, never see those. Anyway, probably most of all suites. This is the grouping. We put a number of people in the rooms to try and simulate more or less full occupancy of the place. And go from there. So, no big parties anywhere in particular. We debated that, putting 20 people in one room. All right, let's talk a little bit about just how do these different models compare a little bit. We've already said some things about this node and arc kind of stuff. And this is all manual at this point. They enter those, and as Erica would mention to me, and then a student working through our classes, it's time-consuming to put that data file together for these couple models. Very nice to have Simulex allow for CAD input, so you don't have to do anything other than provide distances, vertical distances on stairs. Basically, that's all the extra stuff you need to do there. So very straightforward to do the input. How do you do exit selection? Well, the BACnet was the optimization model, so it's automatically sorting people to maybe that closest exit, but the exit that optimizes, minimizes the evacuation time. Exit 89, the user can choose between the shortest route that then the model works with, or you can say, for these people in this room, I want them out this stair. To force the issue a little bit, to block a stair maybe. You have to go through those sort of things as you might do in a fire. And then finally, the Simulex, we saw that distance map with the psychedelic color sort of thing. Environmental conditions, meaning is there any smoke and fire simulation in these models? And the two of them did not have any of that, as I mentioned. Exit 89 has the capability, though, to do apples and apples comparisons. We didn't do any fire modeling for this analysis. There's 25 or so models that exist. I would estimate there are probably four or five of them, maybe 6 of them that do some sort of fire input to the evacuation model. Exodus, the big model, the big name model, that does fire modeling or has that capability. And then finally, behavior. What sort of behavioral issues are involved? And very modestly involved here. This, the BACnet really is no behavior in the way human behavior studies. I mean, you have to provide travel speeds. We're accounting for people movement, but not so much what they're going to do. There is also YouTube body size. X89 with the Austrian, Soviet, American populations. Kind of things you have to say what population you have. And then that deals with velocities. You can also include responsibility here. So if there are pre-movement times, that can be incorporated here, and different pre-movement times for different people can be done in X89. And then finally, occupant types, something I didn't mention here, but the occupant type you can do adults, male, female, children, elderly, to deal with different mobility characteristics, and can also do some pre-movement delays and simulants. But no real behaviors. We think of human behavior, decision making, and let's go wait for a relative, or let's go wait for a coworker. Let me go see if the kids have gotten up. That's not in any of these models. All right. So the results we got. I want to say what we ended up doing. We compared the overall evacuation times first of all for these different models, and tried a couple different variations on them in the way of changing the movement speeds of the people from different correlations by Pauls and Fruit to the names in the evacuation studies that have gone on through the years. Jake Pauls, Canadian, did a lot of work in the 70s, authored the SAP handbook chapters in the first couple editions with a lot of his work. John Fruin from New York, who's really the first premier American researcher in this area. We did some body size changes, so let's look at Austrians and Soviets, not just Americans, and changed how the people would go left or right for the stairs to force that, did some distance map changes, and then also, in addition to looking at evacuation times, look at how they split in different stairs.
I have a question.
Give it.
In these models, are you assuming that everybody gets the alarm at the same time?
Yes.
Okay.
Right.
Jim, do you take into account whether or not, the data has shown in some studies that voice evacuation, will prompt certain responses versus other alarm type signals? I know we've used that lead regress model, and we take into account the delay factor maybe using those pretty important messages versus just a general alarm.
Not specifically, but certainly, we did vary those pre-movement times that you could suggest, why was that? Well, it may have been a different alarm system. There are a couple different velocity values we use, and some of it we might think to be standard because they've appeared in the SFP handbook. So we use some of those, and I'll show you a graph of that in a moment. There are some non-standard values we use as well. That's Fruin stuff that I've mentioned here, though. I mentioned Fruin a couple of times because if you get a BACnet, the free model, Google a BACnet, it'll pop up, download it, and so on. Their default values for movement speeds all based on Fruin's information. I guess in the days before the SFP handbook is probably why that's so, and they've just never revised the model. The SFP handbook values we picked were densities of 5 square feet a person. That puts you here for speeds, or here for the flows going through doorways. So almost optimum conditions going through the doorway that we picked to try and get a best case flow characteristic. We knew we were getting there with that. Speed-wise, to use the same density, though, we had to be here, which if you're in a freewheeling sort of thing and running by the exit, with the crowd, you're going to be not all the way at peak speed. Okay? So we've got these couple of things that we've done from the handbook. And we could have done, and we could still be doing these analysis by doing a range of different densities, and that's the next grad school, I guess. Fruin, one interesting thing about Fruin, if you pick up the Evacuation user's guide, it actually shows you pictures based on his level of service. So this you can kind of say, yeah, crowd flow that I've been in recently, leaving a hockey game or whatever, you know, it was kind of like this or whatever. You can kind of visualize that. It makes it nice, especially as you have to try and relate that to architects. There weren't any architects here, right? Good. Just allow this free range of jokes in. Okay, so with the levels of service, we were in level of service E. To try and get close to that same, with this 4 to 7 square feet a person, we pick 5 for the handbook values to try and be somewhat consistent. All right, so when you use these, what sort of evacuation times do you get? With the BACnet, using the handbook values, SFP handbook from Paul's, you get evacuation time for the building. How long does it take to totally evacuate the place? So we didn't do any phased evacuation. It was a total evacuation, everybody, all at once. 12 minutes, here's 16. All right, just running the default values. Just let them run. Just simply kind of group, blindly throw the times together. Exit 89, it sets its own velocity, so it doesn't care about any of this. It's setting its own, and it's down here at 621. And right away, you start to get a feeling for, hey, you just throw these models together, and that's a difference of 50%. Difference of 50% right there, without trying to, which is also one of the bigger ranges we got. Now, there are some there are issues here. The BACnet requires this sort of speed information for it to travel along every arc to determine how long it takes to go from here to that next room over kind of thing. So it's very dependent. As I say, X89 has it all embedded inside the program, so it doesn't care what sort of numbers you're thinking about. When I did it again. Oh, this is right. That's right. Finally, all right. Now let's go to 6. This is how the body size plays a role in exit 89. So about 800 seconds, 600 seconds for the American, the 621 I showed you on the previous slide. 621. American. The Soviets are up here at a little over 700, and the Austrians are up over 900 seconds. Just by changing that body size, it changes their velocity. The American, Soviet, Austrian, again, those are just labels, right? Just labels, or how big is into it. This square foot, what is that square foot? If I took a shadow of how much room I take, with a bright light shining down on me, that's how much room I would take up. All right. Which is, and we're the typical American bullseye. Who knows typical American from what you see in the newspaper? So we won't go there. Outside. About these hallway nodes, where do you split the hallway in terms of connecting the nodes, connecting the dots, connecting the arcs together to get them to a stair? And then you connect, you have nodes all in each of these rooms, a node here in the hallway, connect these rooms all to the hallway node and down to the stair. Okay? And where do you connect, how do you connect this group of rooms to the stair eventually? That was what we were trying to look at. It doesn't make a difference as to how I connect all the rooms together in this sprinkler network sort of diagram. Okay? We started it, let's do it right down the middle. Kind of default case. We got some answers there, and we ended up sliding it a little bit to the left to see what impact that would make, and I'll show you what we did there. When we compare, first of all, BACnet, it doesn't care where you split the hallway, because it's doing optimization. And again, that's just a reflection of the BACnet, as much as it's a very trivial result. You're getting this optimization, you're getting an almost even split of the people in the two stairs, 556 people in the one stair, 542 in the other, to optimize the evacuation time so that you get the same exact evacuation time using either stair. Okay? That's the aim of that model. 12 minutes. With exit 89, when we ran it the first time, just, that's put it right in the middle, we've had 636 people going this way, 462 going that way. They said, holy smokes, what's going on? That there are so many people. Now there's a conference room on one floor for 50 people, but that's not going to give you 170 people. It makes a big difference in terms of the evacuation times. So now you're starting to say, how I put the input together affects the output. Well, at that point you say, duh. That's a lot of modeling does that, right? The output's dependent on the input. And we were seeing it here in a way that we didn't expect to be quite as emphatic, anywhere near this emphatic. When we moved the split, we ended up getting a more equal distribution here at a lower evacuation time as well. What's the evacuation time of the whole split here? Well, you take the bigger of the two, 621. Right? And I can reduce the evacuation time artificially just by changing that nodal network by a little over a minute. Okay? By clever engineering, some would say. Okay? Right? Not that there are engineering firms who would do that sort of optimization. I'm sure they're clever. They want a license next year.
Jim, as you pointed out, Rob, having done enough of these, you have to be very careful to articulate what your assumptions were, lengthen those travel speeds, effective with the, there's a fairly elaborate explanation to go through before you can show these numbers have some reasonable credibility. Because yeah, you can adjust the numbers, and is there a factor of safety in there? And that's probably one of the biggest things that we see when we, particularly when you do an egress versus tenability, whether it's smoke protected assembly seating, a high rise, or some other assembly space. I think that shows part of the challenge we have from an engineering perspective, saying, yes, we can adjust these numbers. How do you rationalize that, and how do you defend it?
Right. And that's the bottom line to the whole evening discussion. So I'm done.
I won't charge you for it.
But that's the key to it, right? That's the key to it. That these are not just plug-and-play models any more than there is any other fire protection model. That we have to document our assumptions and so on. And it was just interesting how you could do some little adjustments here to these models as it is. And we go through one other one with Simulex. We move those around in the same sort of way. We block the stair from some of the occupants, not all of them, in the one case to try and encourage more of them, because again, we were getting an unequal flow to the two. Where the occupants, in the case of Simulex, were going more to the right stair, if I remember right. Yeah, with the first distance map, map that we did, DM1, just letting Simulex put its own distance map together in the psychedelic color diagram, and we found there were almost 100 extra people using the right exit. And Simulex does that because it knows the one stair is a little shorter than the other stair, considering that landing difference. Now, as you go into a stairway, do you know, hey, this one's 5 feet shorter per floor and I ought to go that way? Of course not. That's not how we select exits. Right? But Simulex knows that. And that's when we move things around a little bit to try to get a flow that was a little more equal without really going into a convoluted way to do that and get a more of an equal back time for the two stairs. When you put it all together, these are the sort of the range numbers we went through with some fairly simple sort of calculations. Now, there isn't any actual fire drill data, unfortunately, or real evacuation data for any of these, for this particular hotel. So unfortunately, we don't have any of that to use as a baseline. If you use it, what's in the S&P handbook, and the setup that's in there, the current edition is by Maurer and Nelson. Perhaps some of you have used some of the hand calculations for stair back times. You get along with 12 minutes. Right? So that's somewhere right about here, on here. Kind of mid-range, right? But for the range on there. But you can get down with the American population and moving that split at exit 89, as we talked about, into a little over 500 seconds. And you can get almost up to 1,000 if you use those heavy Austrians. Beer drinkers, and so on, right? Too many Oktoberfest. This is with the back nav using Fru and slow service. You get almost that same sort of number. So there's a difference, almost a factor of 2, as it turns out. Through just some real simple adjustments. And as Mike has already properly said, the key to this, as in any other model, is you've got to document what are the assumptions, what are we assuming the people to do, when do they start the move. I remember doing a couple of years ago doing a third-party review for, I think it was a mall. And I found myself reading these evacuation counts, and the people were moving as soon as the matches dropped. How did they know that, right? 3 stories away from the store and so on, sort of deal. So you get into those kind of blatant sort of issues like that, let alone some of these other issues that are tough, right? What sort of velocities are being assumed? What sort of let me come back. What sort of densities are being assumed? How crowded is the flow going to be? Right? That's going to make a big difference. Again, all of our analysis was done here. It would be very interesting just to do a sensitivity analysis of these models with the range of densities that you might get in an evacuation, right? At the very least. Anyway, questions from the group of any sort about it? Yeah, sorry.
Question. Do any of the models do any kind of Monte Carlo simulation where they build in all these variables, sort of do a bunch of range variables and come up with a distribution?
Right. There are, Simulants does do some random distribution of the delay times, for example. The building exodus model does some random variables for some of the human behavior sort of aspects. So there are some of them that do that. The exit 89 and the EvacNet, though, the other two are completely deterministic, and they give you the same result every time. So,
Is there a model or 2 or 3 or whatever that are considered to be better than others in terms of their accuracy, effectiveness, and coming up with the right answers, so to speak? Another piece to that question would be, are there certain models that would be considered to be more credible with code officials and people that are approving buildings to be built in their jurisdiction by name, so to speak, by name of the model? Well, I used, the evac model.
Short answer, not that I know of. I mean, in terms of, is there any that's kind of gotten a de facto approval?
Or whatever.
Yeah, I don't know that there's any model that has that de facto approval. A lot of these, they are being used, I understand. I mean, Mike, you talked about using one, and the folks at Hughes do some back modeling, I know. Arup has their own model that they run, and I think RJA has a model of sorts as well. So that, and apparently, they're using these models successfully. Simulex is used by a consulting company in on. So I know that some of these are being used successfully, at least in that commercial market sort of thing. I think, as Mike has already alluded to, but how you judge these in good, better, best sort of thing depends very much on what you're trying to do with them. I think that's the bottom line. If you want to put an evacuation plan together for a high-rise building or a school, the EvacNet model is an evacuation model. It's going to give you the best case answer, sort of thing. Although with some variations, is you can get a better best, right? As I showed you here, or a not so best answer, I guess, depending on who you look at. But it has some of that for a design application in a conservative sort of arena. I'd have some issues with EvacNet. How do you use EvacNet to get you the best case answer in what we usually are dealing with a worst case environment, a lot of our fire protection design. Right? You can pessimize a lot of the inputs to kind of get there in a way, but it's still giving you the best case for the worst case input. That makes any sense.
I think you do have to, sometimes with a lot of the code officials I've experienced, then we do try to, we'll call it a factor of safety, but you try to, like an average, foot speed on a flat surface on a structure is 250 feet a minute. Well, we cut it in half, or we cut it to something where we're saying, based on some of these charts, here's how we come up with those numbers to reflect that. And then at the end of the day, quite honestly, we've had several projects where we've had to run evacuation after the building was occupied. We did the Minneapolis Convention Center where they asked us to do that, and the numbers came in pretty good. We were conservative to do it there. I know we didn't do it on the Excel, but having season tickets for the Wild, I can tell you that we're well below the exit. But you can see where I think it's important, if you err on the conservative side as best as you can with authoritative documents, the better you have a chance, John, of working with code officials saying, do I believe the numbers?
Right.
And, water park, you heard Duke say, hey, I'd like to see you run an evac study now that demonstrates that we could get those kids off the water tower, since we put in a optimized smoke exhaust system based on tenability roofs. We did the calculations and he still hasn't come back yet, but I wouldn't be surprised if he has us do it. And a lot of ones he's shown me, and that helps with some of the numbers.
Right. Some of the models do provide some interesting input. I showed you the Simulx animation, it's pretty crude. Arabs, I think, is kind of a 3D sort of simulation that you see the people building Exodus is a 3D, you see the people walking about and so on. The other ones I don't know. There may be some very good animations for the others I haven't seen. One of the other points I want to bring up in terms of conservative input, what's conservative in one application may not be conservative in another. And in providing this density here, for example, gives you pretty good flow characteristics. You're optimizing the flow out of a doorway. And if your evacuation is driven by going through a doorway, and that's the constraint to the evacuation time, then best case flows are not going to be a best case. Best case flows are going to give you best case answers. If your evac times are dictated mostly by how long does it take to run down a long tunnel, then, and I use this, that would have been pessimized a fair amount because I'm not using a peak velocity. I'm down here at velocities. So what's a best case situation could even vary on what's going to be the dictating factor. And I don't think there are many people with a good enough feeling of any of that at this point that can say that just intuitively. I think you've almost got to run these models a few different times and see, right? And kind of do your own sensitivity analysis. Have I made the conservative assumptions? For sure. And in another few years, I think we'll get the experience base. We'll know that at this point.
But don't you have to be conservative just because of the human behavior? If I step out of a room, I know there's things here and here, that one's flowing, that one's backed up. If I'm down there, but I'm going that way.
Right, that's right. Absolutely. Absolutely. Yeah, these models don't do much in the way of human behavior. We're doing a random delay, gives you a little pre-movement time, but the bulk of the evacuation models, other than building Exodus, don't allow for any any consideration, well, there was the old exit model from NIST that was kind of an early attempt at things. But otherwise, these models don't account for the fact that what's your first action when the bell goes off?
Roll over.
Well, roll over, or if you're in your home, you go look for this thing, right? Because you just got an elbow in the side, sort of, all right, I'll go look for it. And you go look for it for a while. None of the models do with that.
But that's where you like on the Excel, we had to do a life safety evaluation, so we looked at the different occupant characteristics, did we think how many of them were coherent? We tried to, as best as we could, characterize the behaviors of the big model. You go to a Tom Petty concert, they're all stoned off the court. We took those into effect because it's so unpredictable. And I think that's the biggest challenge we have with some of this, since we don't have a grasp on human behavior in a reliable fashion. What can we just build in as conservative factors of safety? It's unknown. And if a guy's going to stand there and watch the fire, it's still probably a theory of evolution.
I was wondering, have they done any testing or anything with the actual data? Because it seems like you're kind of remiss when you don't take into account that human behavior factor.
The bulk of the comparisons to date that have been done have been relative to fire drill stuff. Building Exodus, I keep mentioning, I didn't do the actual runs of them. There are a series of papers that they compared to drills, for example. Now with World Trade Center, there has been some evacuation modeling comparing models with a model, I think again it was Exodus, against the evacuation of the towers, and there were some estimates of timelines there. But you bring up the good point in that there's relatively little comparison at this point available to actual fire data as it is. Even this information that we have here is from drills, for example. And that, how fast we move in a drill, how do you compare that to how fast we're going to move in an actual emergency incident? And that again brings in those factors of safety that are going to have to be applied. Either, though you can argue it's plus and minus, right? In terms of these speeds, are they going to be faster than that because we're more motivated, or slower than that because it's chaotic and smoky and noisy and so on and so forth?
What do any of these models do about disabled people and the fact that they have
Yeah.
leave them behind?
Simulx allows you to derate the velocity of select people, so that can happen. And some of the animations that we saw with Simulx, it does create a logjam, or the one simulation of this that we saw in doing that I didn't report on here at all, but you really see the people stacked up behind the wheelchair in that particular application, or behind the disabled person being helped out. Right? Building Exodus allows. There are a couple of them that allow for. In fact, I guess you could derate the velocity for everybody in a backpack, as an example, assuming everybody with mobility impairment. That's a little extreme. But yeah, that's a good. Right. Good point.
Would you use that same theory then on the models for staged evacuation? Where you're evacuating 3 floors, people are staying in place?
Right, yes, indeed. You could very much do that. There was a student that followed Erica here, in fact, that did some of that in a master's thesis, and doing some phased evacuations with different sized buildings that we were hoping to see, could we justify a particular size, height building when phased evacuation was clearly preferable to total, and we didn't find that clear line, I'll tell you, that I was anticipating. But you can certainly use these models to look at different evacuation strategies, yes.
I guess it raises even more questions for me, as you pointed this out. A couple of thoughts that come to mind is, like, it appears that some of these models are fairly old, relatively old, they're not recent. I guess I'm asking myself, who's paying for the extra research to come up with these new programs? With the faster computers, are there programs that are actually better than some of the older ones that you use here because they're free? I mean, thinking of, how Google is exploding as an example. There's not that large community out there to really pay for this research, other than government. So I guess the question that I'm asking is, where is this going to? How long is it going to take for a model that we can basically download and work on without necessarily, knowing all these ins and outs, but come up with a reasonable answer? Where is this all going to? I'm just thinking that, as fire protection codes have gone from guesswork to full-scale fire tests, not everything, but slowly but surely is getting there. That has taken 20, 25 years or longer. Where is this heading to, and who's going to pay for it? Sorry.
We've got all night.
That's the best.
I'll stay behind for the answer.
Yeah, that's the way to do alcoholic beverages, I think. A couple of the models that are fairly dated, the ones that were developed here in the U.S. that I mentioned anyway. A couple of the newer developments in Simulex and Exodus are both in the UK. It's kind of interesting that they're both offshore. They are being, or at least building Exodus, I know, is aggressively being updated and expanded, and different subroutines looked at compared to any data they can find. They'll know it's drill data so far. I think all of it, looking for those calibrations. I know there's a group at Edinburgh that is still distributing the Simulex code. I assume they're doing things to try to expand it, but I don't know the detail. Otherwise, the U.S. here, it's kind of interesting, right? A lot of our modeling has come from NIST. And NIST supported the Evacuation model 20-some years ago. They supported human behavior research 25 years ago. Basically, it's been pretty removed from the area, I guess. Although certainly post 9/11, they've had people looking at evacuation studies and these sort of things. Bill Grosshandler, the head of the fire lab at NIST, this week was in a meeting commenting how human behavior and evacuation was a primary area of interest for NIST now. Now, does that translate to dollars to develop a new model? I don't know. I have no idea what's on his plate that way. I know that folks at NIST have been using some of the existing models, and whether they're just going to use those or develop a joint relationship, that I have no idea.
It's going to take a long time before we get some. Could be another 20 years, I guess.
Yeah, well, then again, I think the modeling capability, as in so many areas of our field, the modeling capability is there. The numerics is there, the math equations are there. Do you believe any of the output that comes out, right? Is it any different than playing PlayStation and just getting nice graphics and so on, And that's where the calibration is required to be able to believe what the thing's telling you. Either by running it several times to try and understand the quirks, that's one way to do it, but certainly we need some sort of calibration data to really get these things to a point that, yes, we can understand them, we believe them, they're credible, and we go from there.
Anybody else? Any more questions? Everybody looks to be going home, I think. Well, I would like to thank you very much for coming out and presenting us with this. Well, I think that a great deal of value in these presentations is to make us all understand that there is more to it than what we see in front of our eyes every single day, that there are other people working on other developments of our industry, and I think it sort of all ties together. I think that's the great value. It's not that we're all necessarily going to run out tomorrow and run some models, because it sounds like it's very time consuming, and maybe only grad students have that kind of time. Maybe don't, but force into it. Nevertheless, thank you all for coming, and leave your badges behind, and thank you very much for being here presenting this.